Hello. In this video we're going to look at the structural approach to credit risk. The structural models have underlying variables that give meaning to default. So in the sense that when default happens, we can understand what is the economic reason for that. This is by contrast with so-called reduced form models, where the default event is just a statistical event that happens now and then, and there is no economic reason for underlying intuition for it to happen. All right, the main model we're going to look at is Merton's 1974 model. Merton was, or he still is, one of the most influential people in finance. He has produced a lot of important papers, and this paper that we're going to look at now is the central workhorse in credit risk. Okay, just like you have the Black-Scholes model in option pricing, which actually some people say should be called the Black-Scholes-Merton model, because Merton was also very important for that model. But like the Black-Scholes model is the workhorse, the central model in option pricing. This Merton 1974 model is the central, the workhorse model in credit risk. All right, so let's start. Let's jump to the model. The assumptions of the model are basically two assumptions, and let me show that with a figure here. So the first assumption is the following. The first assumption is to make the firm as simple as possible. So you can think of a firm that has some assets with a value V, and then on the right hand side you have equity denoted by S for stock, for share or stock here, and debt is as simple as possible, meaning it's a zero coupon bond that is going to pay F at maturity, capital T, and today has some price B. Okay. So why is this a model of credit risk? Well, because this debt that you see here is risky, in the sense that if, when we get to the maturity date, capital T, the value of the assets is not enough, is very small, more precisely, it's less than F, then it is optimal, it is rational for shareholders to default. Right? They choose to default because they rather just give the assets to the bondholders than have to pay a larger amount F. Okay, so that's assumption number one, a very simple capital structure. Assumption number two is an assumption to specify what is the probability that we observe low value for V. So more precisely, what Merton does is to assume that the value of the assets follows a geometric Brownian motion, which is this process that you see here. So if you have seen this before, you're familiar with it, but if not, intuitively what this is doing is basically just the following. So this figure here shows the value of the assets as a function of time. The value of the assets starts at some value, some known value, given value, V0 today. And what this is going to do is this is going to specify how the value of the assets evolves from today until the maturity date of debt, which is this same T here. Okay. So on average, the value of the assets will evolve through here, like this, with this expression. But this is generating many possible paths for the value of the assets. So it may go like this and end up here. It may go like this and end up here, or it may go down and end up here. It may go very down, very low, and end up here. So all these possible paths. So in other words, what this is doing is generating a bunch of different possible outcomes at this date, or distribution of possible values, right? Debt has a face value of F, which is fixed and does not change as we go through time. So it's always this number here. So basically what we are saying is that there is the possibility of default when V ends up below F. So the probability of default is the probability, it's the probability that corresponds to this mass here, right? It's the probability that the V is below this critical value of debt. All right, so that's the second assumption of the model. So basically what we have to do now is just to actually compute this number. What is this probability? So let's go back to the handouts. All right, so this is the GBM again. This is the solution to that. And here, what we can do to actually determine that number is basically given this, just take logs of this expression on both sides. The log of V over Vt over V0 is what we would call the continuously compounded return on the assets. And given that previous model, it has a normal distribution with this mean and this variance, right? If we have a normal distribution, we can always standardize it by subtracting from the random variable. We can subtract the mean and divide by the standard deviation, and that ratio becomes a normal 0, 1, a standard normal distribution. So to compute the probability of default, we basically just follow these steps. We wanted the probability of V ending up lower than F. I can transform it like this and then like this to make it look like this standard normal distribution that I have here. So basically what we're saying is that the probability of default is just the mass, the tail of the normal distribution up to this critical value defined here. So this example just puts some numbers into these variables. Let's go back again to that figure before, where you have the solution for that. It's here, down here. So you just plug in the numbers that are given. The face value is 70. The initial value of the assets is 100. So over here, the mean mu is 0.1. The standard deviation is 0.2. So plug in the values and you get this critical value for the normal 0, 1. Look up in a normal distribution table or use your calculator or a computer, anything to get this mass of the normal distribution up to minus 2.183, and you'll find that the number is this. So there is a 1.45% probability that the firm will default. The mass here, it's 1.45%. Okay, going back to the PDF. That's the probability of default. And now the second important result of this Merton's model is actually to price the bond. Okay. So the intuition here, the genius of Merton is to relate the bond price to option pricing. And to look at that, you can look through this, or let me try to make the connection in a slightly different way. These are all equivalent ways of doing the same thing, but hopefully here it will be a bit more clear. So how do we relate the value of debt to the value of options? So the payoff, if you hold the debt of the firm, this is the payoff. Basically, if at the maturity date the value of the assets is high, the bondholders get whatever it's promised, which is the value F. This should be F here as well. It's F. The horizontal value here, it's F. If the value of the assets is too low, namely here, then shareholders choose to default, meaning that bondholders only get what is left. Okay, so they get the value of the assets. So this 45-degree line here. So the question now is, what is the type of option that looks like this? Well, the option that looks like this, it's a short put. The short put is this one here. It's almost what I want, but not in the right level, right? So this is at 0 rather than being up here at F. You were not seeing my mouse before, but this is it now. So I was saying that the short put has the right shape, looks like this, but it's not on the right level. So to make this go up, I need to add to it F. So I need to add this constant amount F. So what is the type of asset that produces this? Namely, a payoff F constant that does not depend on the state of this particular firm. Well, it's a riskless bond. Think of a government bond. So this will pay F no matter what happens to the firm. So if I add that bond with this short put, I get the same payoff as having a bond issued by the firm. Okay. So that's the result that you have here. An alternative way of looking at it is from the point of view of a bank that is giving a bond, that is giving a loan to the firm, which is the same as buying a bond. So if the bank gives a loan to the firm and at the same time buys a put option on the firm, then it gets the final result is a risk-free asset. So in other words, this strategy that you see here must give you the risk-free return, which is this I here. And moving the P to the other side, this is saying is that having a risky bond on the left-hand side is the same as having a risk-free bond, which would have this price, the present value of the cash flow at the risk-free rate, and being short a put option. Okay, so the sign here may be a bit confusing, but the idea here is that this sign here is the opposite of this sign here, which is a plus, or this sign here that is a plus. And these signs here are the sign I'm putting as a plus sign, the point of view of the investor. I'm buying the corporate bond, or I'm buying the government bond. The put has the minus sign, saying that I am shorting the put. If I am shorting the put, it means I am selling the put. If I am selling the put, I am getting money from selling the put. So this sign has to be the opposite sign of the investment, of being long in the risk-free bond or being long in the corporate bond. Right, so that's where this minus comes from. So now I just have to determine what is the put price. Well, but now I'm back to option pricing. So what Merton does here is just to use the Black-Scholes formulas. Well, with just a small twitch, which is the following. The Black-Scholes formulas are used normally to price options on stocks. Now what we're doing is pricing an option, a put option, not on the stock, but a put option on the firm. More precisely, the underlying asset to this put option is the assets. So what you see here is the usual Black-Scholes formula for a put option, but where you would see a stock price here, instead you see the value of the assets, because this is the underlying now. And the strike price is the F. D1 and D2 are the usual formulas for D1 and D2, the usual Black-Scholes formulas, again with V instead of the stock price. Okay. But I mean, now it's just you just need to plug in the values and get a put price. Right. So this example does that. Checked that you can get these numbers. So D1 and D2 using these formulas that you see here, and then plugging the D1 and D2 here, computing the normal values and so on, you get the put price here. And then once you have the put price, you just use the put price here, and the risk-free debt is this one, and this would give you the corporate bond price that you have here, right? So then we can do something more with this Merton's model, which at this point is not very obvious why we want to do this, but this will be actually very important for the next model that we'll talk about the next chapter. So what we're going to do now is to relate equity to options as well. Right, and going back to the figure I had here before. So now what we are asking is, what is the type of option that looks like equity? Well, equity looks like this, right? Equity, if the firm value is low, shareholders default, so they get 0. If the firm value is high, above F, shareholders choose to pay the debt, namely to subtract F, and continue with what is left. So their payoff after paying the debt is just what is left, this 45-degree line. Well, and this obviously looks like a long call option, right? So I can compute the value of equity like I compute the value of a call option. Again, I have to be careful that the option I'm talking about now, the call option I'm talking about now, it's not written on the stock. It's written on the value of the asset. So this formula here is the Black-Scholes formula, but taking into consideration that on the left-hand side we usually would call this a C for the value of the call option. Now what we're saying is that the value of the call option is the value of the stock. And on the right-hand side, the underlying is V and not S. So that's what you see here in V. And the strike price is F, the face value of that. And then in D1 and D2 also you need to change the usual formulas for this V and F. Okay, but I mean it's the same D1 and D2 that you have from up there. You just compute this new expression and that would immediately give you the equity price. So finally, we can also use the model to compute the spread on debt. At this point, there is nothing new here. This is just a different way of looking at the results of the model that we already have. Okay. So how do I compute a spread? Well, the spread is just the difference between the yield to maturity on the bond and the risk-free rate. So first I need to compute the yield to maturity on the bond, which is computed in the usual way with continuous compounding. So this y becomes it's the y that comes from this equation. Once I get that y, I can subtract the risk-free rate and I get the spread. So that's one alternative. The second alternative is just to write that same spread directly as a function of these initial values of the problem, right? So I can either use this approach, number one, or use this approach, number two. Both give me the same spread. All right, and so here you have this last example where you compute the spread either through the first approach or the second approach. All right, that's it.